Let's talk about computing definite integrals using only geometry and no fundamental theorem of calculus. So I have three examples in this video. The first one you can see right on the screen. We're asked to compute the integral from 0 to 3 of x plus 1. So what this means physically, you can see the graph of y equals x plus 1 shown here, is we're computing the net area under y equals x plus 1 between the x values of 0 and 3. So we're talking about the area of this little shape here. All right, so we need to get a little bit creative. We are going to chop this area up, at least the way that I see it, into a rectangle on the bottom with a triangle on top. And we'll compute those areas separately and just add them together for our total area. All right, so for this rectangle down here, its area is its length, which is 3, times its height, which is 1. So the area of that rectangle is 3. And then we'll also do the area of this triangle up here. For a triangle, the area formula is 1/2 base height. So that would be 1/2 base of this guy is 3. And then the vertical height goes from 1 to 4. So the vertical height is also 3. And we get 9 over 2, which is 4.5. So that means our integral is equal to 3 plus 4.5, which is 7.5, or you could do this as fractions, and that would be 15 over 2. All right, so sometimes in these problems, will we interpret the definite integral into its like physical meaning for area? We have a lot of rectangles and triangles. The only other shape that may come up in these problems, we can see in the second example, which is a half circle. So here we have the definite integral from -2 to 2 of this function square root of 4 minus x squared. So the square root of 4 minus x squared is pre-drawn here. What this is, like if we square both sides and then add the x squared onto the left, we have x squared plus y squared equals 4. So what we're really looking at when we have just positive root 4 minus x squared is the top half of this circle with center at the origin and radius 2. If we had y equals negative this square root, it would be the bottom half of the same circle. All right, so if we want the area between x equals -2 and x equals +2, it's just this whole half circle here. It's always the area between the curve and the x-axis. All right, so this is going to be half the area of the full circle. And because we're not adding different areas together, I can just go straight to my answer computation. So 1/2 the formula for the area of a full circle, which would be pi r squared, and we're doing half of it because it's just the top half of the circle. All right, and then we go back and say, well, what is the radius of this circle? It appears to be 2. So we have 1/2 times pi times 4, which comes out to a total of 2 pi. All right, so the only geometric shapes that will come up, we can see on the screen here, you've got your half circle, rectangle, and triangle. So there's one, well, actually, this last example has two other kind of tricky layers to it. So in this last example for the video, we're asked to compute the definite integral from 0 to 3 of 2 minus x. So one thing that is tricky about this is that the graph is not provided. So we are going to sketch the graph ourselves and then put it together. So let's do that first. 2 minus x is y equals -x plus 2. If we see it in that order where we just switch the 2 and the -x, we can see it's a straight line with y-intercept at 2 and slope -1. And the fact that it's a straight line means if you can plot any 2 points that are on it, just connect them with a straight line and you're good. For example, if I plug in x equals 0, I get 2. So 0, 2 is on this line. And if I plug in x equals 2, I get an output of 0. So this is y equals negative x plus 2. Okay, so the other tricky thing about this particular problem is that if we are using x values from 0 to 3, we are computing the area of this triangle here all the way to this 3 here. And there's a bit of area, this little triangle here, that is below the x-axis. So in these problems, when we're doing any definite integral, any area between the curve and the x-axis that's below the axis like this counts as negative area in the total. So we're still going to do our normal thing, which is compute the area of these two triangles just using 1/2 base height. But then when we add them together, the piece in red will kind of subtract off the total instead of adding. So we're not doing total area, we're doing net area where the red counts negatively. Okay, so for each of these, we'll do 1/2 base height. 1/2 for the blue here, the base is 2. And the height is also 2. So this positive area comes out to 2. For this little triangle down here, this at x equals 3 is not one of the points that I had plotted. So I'm just going to quickly double check the location of this point. It looks like it's at y equals -1. We'll double check. -3 plus 2 really would be -1. So this little triangle, we have 1/2. The base is 2 to 3, so that's 1. And then the height is here to here, which I double checked really is exactly 1. So this comes out to 1/2. All right, so then for our total, we're going to have 2, and then the -1/2 comes in for the area below. So we get 1/2 or 3/2.